Hello, my friend. Tonight we'll explore strange and beautiful states of matter beyond the solids, liquids, and gases we know so well. This video is meant to ease you into rest. You don't need to stay awake or focus on every word. Simply let the calm explanations guide your thoughts, and if your eyes grow heavy, that's exactly what this video is for. Settle in, get comfortable, and let's begin. Chapter 1. What is matter, really? A quiet framework. When we first learn about matter, the world seems cleanly divided into solids that hold their shape, liquids that flow, and gases that expand to fill their containers. A fourth state, plasma, sometimes joins the list as an ionized gas, the stuff of stars and lightning. That schoolroom picture is not wrong, but it is incomplete in ways that become decisive the moment we ask how and why matter organizes itself, why it changes form, and how new states emerge that defy those basic categories. A careful framework begins not with labels, but with the idea that matter is a set of underlying constituents interacting through fundamental forces, and that what we call a state of matter is a collective pattern those constituents adopt when conditions such as temperature, pressure, and density fix the balance between energy and entropy. At a microscopic level, ordinary matter consists of atoms built from nuclei of protons and neutrons surrounded by electrons. Protons and neutrons are themselves composites of quarks bound by gluons, while electrons appear elementary at the scales relevant to chemistry and materials. Electromagnetism dominates the behavior of atoms and molecules in everyday matter, setting bond lengths and crystal structures and giving rise to rigidity, viscosity, and conductivity. Gravity structures matter on astronomical scales, but is negligible in setting the structure of a salt crystal or a drop of water. The strong and weak nuclear forces mostly reveal themselves inside nuclei or in the cores of stars and neutron stars. This hierarchy of forces hints at a central idea. A state of matter is never defined once and for all by the constituents alone, but by which interactions are active and at what scale they influence collective behavior. Quantum mechanics enters immediately. Electrons and nuclei are quantum objects, and many macroscopic properties are quantum consequences writ large. Electrons are fermions, particles that obey the Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state. That single rule explains chemical structure, the band theory of solids, the existence of metals and insulators, and the degeneracy pressure that props up white dwarfs. By contrast, atoms with integer spin can behave effectively as bosons. Bosons do not exclude one another and can condense into a single quantum state, leading to Bose-Einstein condensation and superfluidity when temperature is driven low enough. The difference between fermionic and bosonic statistics is not an add-on to the notion of a state of matter. It is foundational because it determines what kinds of collective order are even allowed. A macroscopic sample contains a vast number of microscopic degrees of freedom. We do not track each molecule. Instead, we compress information into thermodynamic variables like temperature, pressure, and chemical potential. These variables emerge from statistical mechanics, which connects the microscopic world of quantum states to the macroscopic world of measurable properties by counting the ways a system can be arranged while remaining consistent with its constraints. Entropy quantifies that count. At equilibrium, a system typically adopts the macro state that maximizes entropy subject to conserved quantities, or equivalently minimizes an appropriate free energy that balances internal energy against entropy penalized by temperature. In this language, a state of matter is an equilibrium pattern that minimizes the free energy given the external conditions. Phase transitions occur when this minimum changes its character as a control parameter varies. If water is cooled at 1 atmosphere, the free energy minimum associated with the liquid ceases to be the global minimum near 0 degrees Celsius, and the crystalline arrangement of ice becomes favored. That simple example already shows why symmetry matters. A liquid is invariant under continuous translations and rotations. A crystal breaks those symmetries by selecting a periodic arrangement and specific orientations. Landau's insight was to characterize phases by an order parameter that vanishes in the high symmetry phase and becomes non-zero when symmetry is broken. Although many of the most interesting modern states of matter are not described by simple local order parameters, the symmetry viewpoint remains powerful. It tells us what kind of excitations and responses a phase can support and how transitions may proceed. There are several kinds of phase transitions. In a first-order transition, the order parameter jumps and latent heat is released or absorbed, as when ice melts. In a continuous transition, the order parameter grows smoothly from 0 and fluctuations occur on all scales. Near such critical points, systems forget their microscopic details and display universal behavior. Liquids as different as helium and xenon, magnets with different lattices, and even binary alloys share critical exponents that describe how observables diverge or vanish as the transition is approached. This universality can be understood through renormalization ideas, in which one repeatedly coarse-grains the system by averaging over short-distance fluctuations, seeing how the effective theory flows as the scale changes. Fixed points of this flow govern the universal behavior. In practice, this tells us that a state of matter is partly a question of scale. What looks like a uniform magnet at long distances is a swarm of fluctuating spins at short distances, and what looks like a smooth fluid is a dance of molecules. The microscopic degrees of freedom of a phase often reorganize themselves into emergent collective excitations, which behave like particles even though they are not fundamental. A crystal supports quantized vibrations called phonons. A magnet supports spin waves. A superconductor supports quasi-particles that are mixtures of particle and whole character. These quasi-particles are not linguistic flourishes but measurable actors, carrying heat, spin, and charge, and scattering like particles in experiments. In many phases, the low-energy physics is fully captured by a handful of such excitations and their interactions. Not all states of matter are defined by symmetry breaking. In some, the distinguishing features are global and topological rather than local. The fractional quantum Hall states are the classic example. A two-dimensional electron gas in a strong magnetic field and at low temperature can form a fluid whose excitations carry fractional charge and obey anionic statistics. The quantization of Hall conductance and the robustness of edge currents are not tied to an order parameter, but to topological invariants that cannot change without closing an energy gap. More recently, topological insulators and superconductors have broadened this idea. They are insulating in the bulk, but host protected conducting states at their boundaries, again enforced by topology and symmetry. This topological perspective expands the framework for states of matter beyond which symmetry is broken to which global quantum structure is realized. Matter can also be ordered without being crystalline. Glasses are rigid like solids but lack long-range periodic order. They form when a liquid is cooled or compressed so quickly that it avoids crystallization and falls out of equilibrium. Its viscosity grows so large that it behaves like a solid on laboratory timescales. The glass transition is not a sharp equilibrium phase transition, but a kinetic arrest, and it raises deep questions about whether there is hidden order on subtle scales, or whether the notion of a state should be broadened to include materials whose defining property is the impossibility of reaching equilibrium within the age of the universe. Equilibrium is a central assumption of traditional thermodynamics, but much of the matter we care about is driven far from equilibrium. A flame, a living cell, and a laser are all examples where energy is constantly supplied and dissipated. In such systems, steady states can arise that have no equilibrium analogs, with long-range order sustained by currents and feedback. Even in electronics, non-equilibrium can define phases. For example, the lasing state is a population inversion that yields coherent light. The framework for states of matter is therefore widening to include driven, dissipative phases characterized by new kinds of order and fluctuations. It is useful to connect these ideas to the familiar textbook phases. Solids are phases where atoms or molecules occupy fixed positions relative to one another, often in a periodic crystal lattice. Liquids have no long-range positional order. They flow because molecules can rearrange without paying a large energetic penalty. Gases have low density and weak interactions. Their molecules move freely and fill the available volume. Plasmas arise when electrons are stripped from atoms, leaving a soup of charged particles whose collective behavior is governed by electromagnetic fields. Even here, the framework of order, symmetry, and excitations applies. Quantum mechanics layers further structure on this picture. In metals, the electronic states form bands due to the periodic potential of the crystal lattice. Whether a material conducts depends on the filling of those bands. In superconductors, electrons pair up into bound states that condense into a coherent macroscopic quantum state with zero resistance. In superfluids, atoms flow without viscosity through narrow channels, sustaining persistent currents. These behaviors are extreme, but they are logical consequences of the same principles: quantum statistics, interactions, and the organization of many body states under constraints. A complete framework must also describe how matter behaves under extremes that only nature can produce. In the center of a white dwarf, electrons are packed so tightly that degeneracy pressure balances gravity. In neutron stars, neutrons form a superfluid and superconducting protons thread magnetic flux tubes, while densities approach those of atomic nuclei. At still higher energies, the distinction between protons and neutrons dissolves, and quarks and gluons roam in a strongly coupled plasma that filled the early universe. These examples show that states of matter extend seamlessly from a lab cryostat to a cosmic collision. The variables change: density instead of pressure, magnetic field instead of strain, but the conceptual apparatus of phases, transitions, degrees of freedom, and emergent behavior remains the same. Disorder complicates but does not break the framework. Real materials have impurities and defects, and these can localize electrons, pin vortices, and broaden phase transitions. Yet many phases remain well defined in the presence of weak disorder, and some, such as topological phases, are even protected by it. In low-dimensional systems, fluctuations and disorder play enhanced roles, forbidding some kinds of order at finite temperature while allowing quasi-long-range order where correlations decay as a power law. In building a narrative that will eventually include strange states of matter, it is helpful to gather the threads. A state of matter is a collective organization of many microscopic constituents governed by interactions and constraints. It is characterized by the symmetries it preserves or breaks, by the excitations that carry its low-energy dynamics, and by global structures that can be topological as well as local. It is selected by the minimization of an appropriate free energy when equilibrium is achieved, or by the establishment of steady balances between drive and dissipation when it is not. It is sensitive to scale, to dimensionality, and to disorder. Each new state of matter is not merely a name, but a new solution to the same problem. How many things, constrained by the same microscopic laws, choose to arrange themselves when they are left alone or gently steered? This framework has practical consequences. It guides how to search for new materials by tuning parameters such as composition, pressure, and temperature. It tells experimentalists what signatures to seek, whether in transport measurements, scattering experiments, or spectroscopic probes. It suggests why certain applications, such as lossless power transmission or topologically protected qubits, might be feasible and how to recognize the obstacles that remain. The vocabulary of phases and transitions is a common language that allows insights to move quickly across contexts. Finally, an honest framework acknowledges its limits. Not every material falls neatly into equilibrium categories. Glasses remain a challenge. Strongly correlated electron systems can defy simple quasi-particle pictures. Non-equilibrium phases are only beginning to be cataloged with the same precision as their equilibrium cousins. Quantum mechanics at the smallest scales and gravity at the largest scales still resist unification within a single theory, and the states of matter that would exist at the Planck scale remain conjectural. Yet these limits are productive. They drive new techniques, from quantum simulation with ultra-cold atoms to high-intensity lasers and particle collisions that recreate extreme conditions on demand. The framework is not a closed book. It is a set of principles that continues to expand. If you step back, there is a humbling theme. Matter is not a fixed thing. It is a repertoire of possible arrangements, and the universe is the stage on which those arrangements play out. To learn what matter is, really, is to learn how context chooses and how patterns emerge. In that sense, the framework is more than a chart of phases. It is a map of how reality organizes itself. And in a softer existential register suitable for sleep, it is a reminder that even the most solid things are stories told by countless unseen parts, moving together, finding order for a while, then changing again. Chapter 2. Plasma, the fourth state and the most common one. When we think about matter in its everyday forms, we naturally picture the objects around us: solid ground beneath our feet, liquid water flowing in rivers, gases like the air we breathe. But if we look outward into the universe, this hierarchy flips. The overwhelming majority of ordinary matter is not solid, liquid, or gas, but plasma. Stars, nebulae, and the tenuous intergalactic medium are all made primarily of plasma, a state of matter that is both familiar and alien. It surrounds us in the sun's radiance and flickers briefly on Earth in lightning, auroras, and controlled laboratory experiments. To understand plasma is to shift perspective from the local and stable to the energetic and collective, where charged particles interact in ways that make them far more than a simple extension of gases. At its essence, plasma is a state of matter in which atoms have been ionized, meaning that some or all of their electrons are stripped away. This creates a mixture of free electrons and positively charged ions, which together form a medium that responds to electric and magnetic fields in ways neutral gases cannot. What makes plasma so distinctive is not only the presence of charges, but the collective behavior that arises when those charges interact through long-range electromagnetic forces. Unlike the collisions of neutral atoms in a gas, which are mostly local and short-ranged, the forces in a plasma extend across large distances, binding the motion of countless particles together into waves, currents, and structures. This makes plasma both fluid-like and field-like, capable of supporting oscillations and instabilities that are foreign to other phases of matter. The abundance of plasma in the cosmos is staggering. Our Sun, like all stars, is a colossal sphere of plasma sustained by nuclear fusion in its core. The temperatures in stellar interiors, reaching millions of degrees, are sufficient to tear electrons from atoms completely. Even in the cooler outer layers, matter exists as partially ionized plasma, shaping the photosphere, chromosphere, and corona. The solar wind, which streams outward from the sun at hundreds of kilometers per second, is a continuous outflow of plasma filling the heliosphere. On larger scales, galaxies contain vast plasma halos and jets expelled by active galactic nuclei. Even the space between galaxies is suffused with plasma at temperatures of millions of degrees, though at extremely low densities. By mass, plasma is the dominant state of visible matter in the universe. On Earth, plasma is less dominant but not absent. Lightning is a natural plasma discharge where intense electric fields ionize air molecules, creating a conductive channel that glows with energy. The aurora borealis and australis are produced when charged particles from the solar wind collide with atoms in the upper atmosphere, temporarily ionizing them and producing characteristic emissions of light. In laboratories, plasma appears in devices ranging from neon signs to plasma televisions, where ionized gases produce glowing discharges. Industrial processes use plasma for etching and coating materials, and controlled fusion research creates hot plasmas in magnetic confinement devices and inertial confinement experiments. Though transient on Earth, these examples illustrate how plasma straddles both the natural and the technological. Plasma has properties that separate it sharply from ordinary gases. One defining feature is electrical conductivity. Because it contains free electrons and ions, plasma can carry currents and generate magnetic fields. This conductivity is not absolute, but depends on temperature and density. Even partially ionized plasmas can behave differently depending on their degree of ionization. Another hallmark is the ability of plasma to shield electric fields through a process called Debye screening. In a plasma, a test charge placed in the medium will be surrounded by a cloud of oppositely charged particles that partially cancel its field beyond a characteristic distance, known as the Debye length. This length sets the scale below which electrostatic interactions matter, and beyond which the plasma appears quasi-neutral. Quasi-neutrality is a subtle but essential concept. On large scales, a plasma has nearly equal numbers of positive and negative charges, but on small scales, it can sustain charge separations that give rise to complex phenomena. Plasma also supports a rich zoo of collective oscillations and waves. Because electrons and ions can move relative to one another, they can oscillate at characteristic frequencies set by their mass and charge density. These oscillations can couple to electromagnetic waves, producing plasma waves, ion acoustic waves, and magnetohydrodynamic modes that propagate along magnetic field lines. In astrophysics, such waves transport energy across stellar interiors, shape the dynamics of solar flares, and accelerate particles to cosmic ray energies. In laboratory plasmas, waves are used deliberately to heat and stabilize fusion plasmas, or they may appear as instabilities that limit confinement. The wave nature of plasma highlights its role as a collective medium where the actions of individual particles are inseparable from the self-generated fields they sustain. Magnetic fields play a special role in plasma. Because charged particles spiral around magnetic field lines, their motion becomes constrained, giving rise to anisotropic transport. A plasma threaded by a magnetic field behaves differently parallel and perpendicular to the field. This leads to structures such as magnetic flux tubes, current sheets, and reconnection zones where field lines break and reconnect, explosively releasing stored magnetic energy. Solar flares and coronal mass ejections are examples of magnetic reconnection on cosmic scales, while similar processes occur in planetary magnetospheres and in laboratory devices. The study of magnetized plasma, known as magnetohydrodynamics, treats plasma as a conducting fluid coupled to electromagnetic fields. This framework has successfully explained phenomena from sunspots to the collimation of astrophysical jets, while also guiding engineering and fusion research. Temperature and density define different plasma regimes. At high densities, such as in stellar interiors, collisions are frequent, and the plasma behaves like a nearly perfect fluid. At low densities, such as in the solar corona or interstellar medium, collisions are rare and collective electromagnetic effects dominate. Laboratory plasmas often lie in intermediate regimes where both collisions and collective processes matter. Temperatures span an enormous range. Laboratory glow discharges may reach only a few electron volts, while fusion plasmas exceed tens of millions of degrees, and astrophysical plasmas can reach billions of degrees in supernova explosions. Despite these differences, the same principles, ionization, quasi-neutrality, electromagnetic coupling, unite them. Understanding plasma is not only a matter of description, but also of control. In fusion research, the challenge is to confine plasma long enough and at high enough temperature for fusion reactions to release more energy than is put in. Magnetic confinement, as in tokamaks and stellarators, uses strong fields to guide plasma away from material walls. Inertial confinement, as in laser-driven implosions, relies on compressing tiny pellets of fuel to extreme conditions before they can expand. Both approaches push plasma physics to its limits, requiring mastery of instabilities, turbulence, and interactions between light and matter. Progress has been steady but difficult, and fusion remains one of the grand challenges of applied plasma physics. Astrophysical plasmas offer laboratories far larger than any on Earth. In the Sun, turbulent convection and magnetic fields give rise to the solar cycle, with its periodic increase and decrease of sunspots and flares. In pulsars, plasma is accelerated to relativistic speeds, producing beams of radio waves that sweep across space like lighthouses. In accretion disks around black holes, plasma spirals inward, heating to such temperatures that it emits X-rays and launches jets traveling near the speed of light. These environments test plasma theory under extremes of density, temperature, and gravity, offering insights that laboratory experiments cannot provide. Observations of plasma in space thus play a dual role. They are both cosmic phenomena to be explained and natural experiments that extend our reach. Plasma physics also bridges fundamental physics. It embodies the interplay between particles and fields that lies at the heart of electromagnetism and quantum theory. The behavior of plasma waves can be described using classical equations, yet quantum mechanics sets the conditions under which ionization occurs and determines how radiation interacts with plasma. At very high densities, quantum degeneracy modifies plasma properties, as in white dwarfs where electrons form a degenerate plasma. At ultra-high energies, as in the early universe, quarks and gluons formed a plasma beyond ordinary matter. In this way, plasma is not a single state, but a family of states defined by context, unified by ionization and electromagnetic collectivity. Despite decades of study, plasma still resists complete mastery. Its richness lies in its nonlinearity and turbulence. Small fluctuations can grow into large structures, ordered fields can suddenly reconnect, instabilities can cascade into turbulence that redistributes energy and momentum. This complexity makes plasma beautiful, but also challenging to predict. Numerical simulations using supercomputers model plasma on scales from laboratory discharges to galaxy clusters, but even the best models must approximate certain processes. Experiments complement these simulations, probing plasma with lasers, probes, and spectroscopy. The combination of theory, computation, and experiment is slowly peeling back layers of complexity, revealing patterns that echo across scales. The pervasiveness of plasma in the cosmos suggests that our everyday experience with solids and liquids is parochial. On Earth, conditions favor condensed phases and neutral gases, but these are exceptions rather than rules. To grasp plasma is to grasp the universe as it is, not as we experience it locally. Plasma is the state of matter that shines as starlight, sculpts magnetic storms, and fills the space between galaxies. It is both ordinary and exotic, familiar in its glow, yet alien in its dynamics. In reflecting on plasma, there is room for a quiet, existential note. The very light by which we see the stars is the product of plasma. Photons released as charged particles collide, fuse, and radiate. Every sunrise is plasma at work. If matter organizes itself into countless possible patterns, plasma is its most expansive expression, stretching across galaxies and epochs. To know plasma is to know that the universe burns, breathes, and glows not in solid or liquid form, but in a restless state where order and chaos mingle, and where, for a time, the cosmos is alive with light. Chapter 3. Bose-Einstein condensates, matter near absolute zero. When matter is cooled, it slows. Atoms and molecules, which jostle and vibrate vigorously at room temperature, lose energy and become more ordered. In solids, they settle into lattices. In liquids, they flow sluggishly. In gases, they condense to liquids as their motions diminish. But there is a limit to how far this cooling can go. And that limit is absolute zero, the point at which thermal motion vanishes. Long before scientists had the experimental tools to reach such extremes, theorists wondered what would happen if matter could be brought arbitrarily close to that ultimate boundary. The answer, predicted in the 1920s by Albert Einstein and Satyendranath Bose, was the possibility of a wholly new state of matter. The Bose-Einstein condensate. The essential idea behind Bose-Einstein condensation comes from the peculiar statistics that govern quantum particles. In our everyday world, we encounter objects that seem distinguishable and behave according to classical probability. But at the microscopic level, the fundamental constituents of matter are divided into two great families: fermions and bosons. Fermions, such as electrons, protons, and neutrons, obey the exclusion principle and cannot occupy the same quantum state. Bosons, by contrast, are gregarious. They can crowd into identical states without restriction. Photons, the quanta of light, are bosons, and their collective behavior underlies phenomena such as lasers. Atoms, too, can act as bosons if their total spin is an integer, and it was this realization that allowed Einstein to extend Bose's ideas from light to matter. In a gas of bosonic atoms cooled to extremely low temperatures, the particles lose much of their individual identity. Their quantum wave functions, normally spread out and overlapping slightly, begin to overlap so strongly that they can no longer be distinguished. When the thermal energy becomes small compared to the spacing of energy levels in the trap that holds them, a macroscopic fraction of the atoms collapse into the lowest available quantum state. Instead of behaving like a collection of separate atoms, the system behaves as a single quantum entity. This is the Bose-Einstein condensate. Matter that is no longer a set of individuals, but one coherent whole. For decades, the idea was purely theoretical. The temperatures required, fractions of a millionth of a degree above absolute zero, seemed unreachable. Progress came slowly, with advances in cryogenics, laser cooling, and magnetic trapping techniques. By the 1980s, physicists could cool atoms to microkelvin ranges, but it was still not cold enough for condensation. The breakthrough finally arrived in 1995, when Eric Cornell and Carl Wieman at GLE in Colorado and Wolfgang Ketterl at MIT independently created Bose-Einstein condensates using rubidium and sodium atoms. They combined laser cooling, which slows atoms by scattering photons tuned slightly below resonance, with evaporative cooling, in which the hottest atoms are allowed to escape a magnetic trap, leaving behind a progressively colder sample. The results were striking. Clouds of atoms suddenly collapsed into dense, coherent droplets that exhibited interference patterns and quantum properties on macroscopic scales. The long-predicted condensate was real. What makes Bose-Einstein condensates so extraordinary is not simply their novelty, but their properties. In a condensate, atoms lose their individuality. Their momenta and positions are not independent but described by a single macroscopic wave function. This coherence allows condensates to behave like superfluids, flowing without viscosity and forming vortices quantized by fundamental constants. Experiments have demonstrated interference between separate condensates, showing that they possess well-defined phase relationships like coherent light beams. Matter-wave optics becomes possible, where condensates are split, recombined, and manipulated analogously to light in an interferometer. The condensate turns atoms into waves that can diffract, focus, and interfere in ways that defy classical intuition. Bose-Einstein condensates are delicate. They exist only under extraordinary conditions: ultra-low temperatures, isolation from environmental noise, and precise control of interactions. The condensate fraction, the percentage of atoms occupying the ground state, grows as the temperature approaches absolute zero, but shrinks when the system is heated. Because the atoms are neutral, trapping them requires magnetic fields or optical lattices created by interfering laser beams. These traps not only confine the atoms, but also influence their dynamics, making condensates both a playground for fundamental physics and a tool for simulating other systems. Interactions between atoms in a condensate are subtle but crucial. If they did not interact, the condensate would be fragile, prone to collapse under the slightest disturbance. Repulsive interactions stabilize the cloud, allowing it to spread slightly and avoid runaway density spikes. Attractive interactions, by contrast, can destabilize the condensate, leading to collapse or the formation of bright solitons, self-trapped wave packets that balance attraction against dispersion. By tuning interactions using magnetic fields through techniques like Feshbach resonances, physicists can engineer condensates with desired properties, from strongly interacting superfluids to weakly interacting gases. This tunability has made condensates a versatile laboratory for exploring quantum many-body physics. One of the most profound uses of Bose-Einstein condensates is as quantum simulators. Many problems in condensed matter physics, such as high-temperature superconductivity or frustrated magnetism, are too complex to solve exactly and too difficult to model numerically. But by arranging atoms in optical lattices and adjusting their interactions, researchers can mimic the Hamiltonians of solid-state systems and study their phases under controlled conditions. The cold atoms stand in for electrons in a crystal, revealing how order, superfluidity, or insulating behavior emerge. This analog quantum simulation complements digital quantum computing and has already provided insights into strongly correlated systems. Condensates also offer a testing ground for fundamental physics. Because they are macroscopic quantum states, they make quantum mechanics visible at scales large enough to manipulate directly. Interference fringes from overlapping condensates are not abstract. They can be imaged. Quantized vortices can be observed as holes in the density profile. These phenomena confirm the deep principle that quantum coherence, usually confined to photons or microscopic particles, can extend to thousands or millions of atoms. Some experiments even use condensates to explore analogies with cosmology, such as simulating aspects of black hole horizons or early universe phase transitions. In these settings, the condensate becomes a model universe in miniature, where exotic physics plays out in controllable ways. Despite their fragility, condensates are not purely academic. Their extreme sensitivity to perturbations makes them excellent candidates for precision measurement. Atom interferometers based on condensates can measure gravitational acceleration, rotations, or fundamental constants with unprecedented accuracy. Because the condensate's coherence enhances the signal-to-noise ratio, such devices may outperform classical sensors in navigation, geophysics, or tests of fundamental physics. The practical applications are still emerging, but the potential is vast. The creation of Bose-Einstein condensates has also illuminated the boundary between quantum and classical. In ordinary matter, decoherence ensures that macroscopic systems behave classically, with wave functions collapsing under the weight of countless interactions. In condensates, however, coherence survives across macroscopic distances. This challenges our intuitions about where quantum mechanics ends and classical physics begins. Observing condensates forces us to confront the reality that quantum behavior is not confined to the microscopic, but can manifest in systems we can see and manipulate directly. As with other states of matter, condensates exhibit rich dynamics when pushed out of equilibrium. When quenched rapidly, they may form defects such as vortices, analogs of cosmic strings, thought to have arisen during symmetry-breaking events in the early universe. The study of such quenches has revealed universal scaling laws and deep connections between condensed matter and cosmological phenomena. Condensates also support collective modes, such as sound-like oscillations and shape vibrations, that reveal information about interactions and stability. These dynamical behaviors make them as lively as they are delicate. Different atomic species have been used to create condensates, from rubidium and sodium to lithium, potassium, and ytterbium. Each brings unique properties, such as differing scattering lengths, masses, or optical transitions, that allow experimentalists to explore new regimes. Fermionic atoms, when paired into effective bosons, can also form condensates, leading to crossover phenomena between Bose-Einstein condensation and superconductivity. This blurring of distinctions emphasizes the unity of quantum many-body physics, where the same principles reappear in different guises. The search for new forms of condensates continues. Spinor condensates, where atoms carry internal spin degrees of freedom, support complex textures and magnetic ordering. Dipolar condensates, with long-range interactions between magnetic or electric dipoles, produce roton-like excitations and self-organized structures. Exciton-polariton condensates, formed from coupled light matter quasiparticles in semiconductors, exist at higher temperatures and bridge the gap between photons and atoms. These frontiers show that condensation is not limited to a single family of systems, but is a universal possibility whenever bosonic degrees of freedom interact and cool sufficiently. Bose-Einstein condensates thus embody the triumph of prediction and perseverance. They took 70 years to move from theory to reality, requiring the refinement of experimental techniques and the persistence of generations of physicists. Their existence confirms the profound consequences of quantum statistics and demonstrates how new states of matter can emerge from old principles when pushed to extremes. They remind us that matter is not exhausted by the familiar categories of solid, liquid, gas, or plasma, but continues to surprise when we venture toward the edges of possibility. In contemplating Bose-Einstein condensates, one cannot help but sense an existential undertone. Here is matter stripped of individuality, many becoming one, coherence replacing separation. The atoms, once restless and distinct, merge into a single wave that moves as though it were a single being. It is a picture that resonates beyond physics, suggesting that individuality and unity are not opposites but possibilities of the same foundation. In the stillness near absolute zero, matter whispers a truth about the universe, that under the right conditions, multiplicity can dissolve into coherence, and the many can become one. Chapter 4. Fermionic condensates, a different kind of quantum fluid. In the world of quantum statistics, particles divide into two families, bosons and fermions. The distinction is absolute, set by the mathematics of quantum mechanics and the spin of the particle. Bosons, with integer spin, are allowed to share states, piling into the same quantum configuration without limit. This gregariousness is what makes lasers possible, and it is what allowed the creation of Bose-Einstein condensates, where atoms collapse into a single macroscopic wave function. Fermions, with half-integer spin, live by a different rule. They obey the Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state. That exclusion principle explains the structure of the periodic table, the properties of metals and semiconductors, and even the stability of white dwarfs and neutron stars. But it also raises a question. If bosons condense by crowding together, can fermions ever form a condensate? The answer lies in pairing. Although fermions cannot occupy the same state as individuals, they can pair up under the right conditions. A pair of fermions has integer spin and thus behaves as a composite boson. If enough pairs form and move coherently, they can undergo condensation, much like bosonic atoms do. This principle underpins superconductivity in metals, where electrons form pairs known as Cooper pairs that flow without resistance. It also explains superfluidity in helium-3, a fermionic isotope that becomes a superfluid not by direct condensation, but by pairing its atoms into composite bosons. Extending this logic, a fermionic condensate is a state of matter formed when a gas of fermionic atoms is cooled to such low temperatures that they pair and condense into a coherent macroscopic quantum state. The creation of fermionic condensates was one of the milestones in ultracold atomic physics. After the success of Bose-Einstein condensates in the 1990s, researchers turned to gases of fermionic atoms such as potassium-40 and lithium-6. The difficulty was that fermions, unable to occupy the same state, resist compression into low energy levels. Laser cooling and magnetic trapping can bring them into the microkelvin range, but achieving condensation requires them to interact strongly enough to form pairs. Here, a powerful tool comes into play: the Feshbach resonance. By tuning an external magnetic field, experimenters can adjust the effective interaction between atoms, making it either weakly attractive, repulsive, or strongly binding. Near resonance, fermions can form pairs even when their natural interactions would not favor it. With these tools, in the early 2000s, groups at MIT, Duke, and Innsbruck succeeded in creating fermionic condensates. They cooled gases of lithium or potassium atoms to nanokelvin temperatures and tuned the interactions so that atoms paired up. The result was a superfluid state with properties distinct from Bose-Einstein condensates, but equally remarkable: clouds of atoms exhibiting macroscopic coherence, superfluid flow, and collective behavior that revealed the deep unity of quantum statistics. Fermionic condensates are not just copies of their bosonic cousins. Their significance lies in the connection they forge between different regimes of quantum matter. In the weakly interacting limit, pairs of fermions resemble the loosely bound Cooper pairs of superconductors. In the strongly interacting limit, they resemble tightly bound molecules that condense like bosons. The smooth evolution between these regimes is known as the BEC-BCS crossover, named after Bose-Einstein condensation and the Bardeen-Cooper-Schrieffer theory of superconductivity. By tuning interactions across a Feshbach resonance, experimenters can traverse this crossover in real time, exploring the entire spectrum from weakly bound to strongly bound pairing. This makes ultra-cold fermionic gases a laboratory for testing ideas that apply from condensed matter to nuclear and astrophysical systems. One striking property of fermionic condensates is superfluidity. When pairs condense into a coherent state, the gas can flow without viscosity. In experiments, this manifests as the ability of the cloud to sustain oscillations without damping, or to form quantized vortices when rotated. These vortices, with their cores free of pairs, are hallmarks of superfluid order. Observing them confirms that the condensate has long-range phase coherence, a defining feature of superfluids. The study of these vortices, their dynamics, and their stability provides insights into turbulence and collective phenomena in quantum fluids. Fermionic condensates also allow exploration of strongly correlated systems. Unlike ideal gases, where interactions are negligible, near the crossover interactions dominate. The pairs are neither well-defined molecules nor weak Cooper pairs, but something in between. In this regime, simple theories fail, and universal behavior emerges that depends only on general features like density and temperature. The so-called unitary Fermi gas, tuned exactly at resonance, exhibits scale invariance and universal thermodynamics, making it a benchmark for theories of strongly interacting matter. The behavior of this gas informs not only atomic physics but also nuclear physics, where neutrons and stars interact in similar ways. Connections to astrophysics are particularly intriguing. Neutron stars are composed of fermionic neutrons at densities far beyond anything on Earth. Theory suggests that they form superfluid phases, with pairing among neutrons leading to frictionless flow in the stellar interior. Proton superconductivity may coexist, threading magnetic flux tubes through the star. The study of fermionic condensates in the laboratory cannot recreate the extreme densities of neutron stars, but it does provide analogies that sharpen our understanding of pairing, superfluidity, and the behavior of fermions under extreme conditions. In this way, the coldest matter on Earth reflects the densest matter in the cosmos. Fermionic condensates also bridge condensed matter and particle physics. The mathematics of pairing and condensation reappears in diverse contexts, from quark matter in quantum chromodynamics to color superconductivity at high densities. The universality of pairing as a mechanism shows that the exclusion principle does not forbid coherence, but channels it into subtler forms. Where bosons condense directly, fermions must cooperate, binding into pairs that then act collectively. This difference enriches the taxonomy of matter, showing how fundamental quantum rules ripple outward into macroscopic behavior. Experimentally, fermionic condensates reveal new techniques and challenges. Cooling fermions requires circumventing the exclusion principle, which suppresses collisions at low temperatures. Sympathetic cooling, where fermions are cooled via interactions with co-trapped bosons, helps overcome this obstacle. Creating stable traps, controlling interactions precisely, and imaging delicate quantum states all demand ingenuity. Over time, advances in optical lattices, radiofrequency fields, and high-resolution microscopy have refined the ability to manipulate fermionic condensates, making them platforms for increasingly sophisticated quantum simulations. Theoretical studies of fermionic condensates have illuminated phase diagrams rich with possibilities. Beyond the standard superfluid phase, exotic phases may arise, such as polarized condensates, where imbalance between spin populations leads to unusual pairing, or full Differential-Larkin-of-Chinnikov states where pairs form with finite momentum. These phases, long theorized but elusive, may one day be realized in cold atom experiments, revealing new frontiers in the physics of pairing. The possibility of engineering artificial gauge fields and spin-orbit coupling in ultracold gases further expands the landscape, allowing exploration of phases with topological order or unusual symmetries. Fermionic condensates also play a role in precision measurement. Their coherence and sensitivity make them candidates for probing fundamental constants, testing theories of many-body physics, or developing advanced sensors. While still primarily a research tool, their potential for applications mirrors that of Bose-Einstein condensates, and in some respects surpasses it, because fermions include the building blocks of ordinary matter. Understanding their condensation may ultimately inform technologies as diverse as superconducting circuits, quantum devices, or astrophysical modeling. Philosophically, fermionic condensates highlight the creativity of nature under constraint. Fermions cannot crowd into a state directly, yet by pairing they find a path to coherence. The exclusion principle, far from being a barrier, becomes the seed of new structure. Out of limitation emerges innovation. The universe finds ways to create unity even among particles bound to remain apart. In reflecting on fermionic condensates, there is a quiet existential resonance. They are matter transformed by cooperation, individual particles binding in pairs to achieve what they cannot alone. In the coldest reaches of the laboratory, atoms whisper a story of unity forged not by likeness, but by partnership. And if the cosmos itself is sustained by such pairings, in stars, in superconductors, in unseen depths, then perhaps coherence born of constraint is not only a physical truth, but a broader pattern of existence. Chapter 5. Superconductors and Superfluids, Matter Without Resistance. In most situations, motion through a medium comes with a price. Push an object through water, and viscosity resists its passage. Send an electrical current through a wire, and resistance converts part of that flow into heat. These forms of dissipation are not flaws in the laws of physics, but expected consequences of interactions and scattering. Yet in certain extraordinary states of matter, nature seems to suspend the rules. Electrical current can flow forever without fading, a liquid can circulate endlessly without slowing. These are the phenomena of superconductivity and superfluidity, two related but distinct manifestations of matter without resistance. They reveal the profound capacity of quantum mechanics to organize many particles into collective states where dissipation vanishes, replaced by coherence that spans macroscopic scales. Superconductivity was first discovered in 1911 by Heikki Kammerling-Onnes, who had succeeded in liquefying helium and thus could explore electrical resistance at unprecedentedly low temperatures. When he measured the resistance of mercury, he found that at 4.2 Kelvin it did not merely decrease gradually, but dropped abruptly to zero. The current persisted without measurable decay. This was not simply very good conduction. It was something qualitatively new. Over time, it became clear that superconductors also expel magnetic fields, a phenomenon called the Meissner effect. Together, zero resistance and perfect diamagnetism define superconductivity as a distinct phase of matter. The microscopic explanation came decades later. In 1957, John Bardeen, Leon Cooper, and Robert Schrieffer proposed what is now called BCS theory. The key insight was that electrons in a metal, despite being fermions, can form pairs through an effective attraction mediated by lattice vibrations. A slight deformation of the crystal as one electron passes can attract another electron of opposite momentum and spin, binding them weakly into a Cooper pair. These pairs are bosonic and can condense into a coherent quantum state that encompasses the entire material. Once in this state, the pairs move collectively. Scattering that would normally disrupt individual electrons now requires breaking pairs, a process that costs finite energy. As long as the system is kept cold enough, resistance is impossible because no excitations are available to absorb momentum. Superconductivity manifests in remarkable ways. Persistent currents can flow indefinitely in closed loops. Magnetic fields are expelled from the interior, yet concentrated into quantized flux tubes in type II superconductors. Quantum interference effects, such as those observed in Josephson junctions, allow phase differences in the superconducting wave function to drive oscillating or constant currents. These properties have led to practical applications. Superconducting magnets power MRI machines and particle accelerators. Superconducting quantum interference devices measure magnetic fields with extraordinary sensitivity, and Josephson junctions form the basis of some approaches to quantum computing. Despite these achievements, the technological potential of superconductivity remains partly unrealized because maintaining the ultra-low temperatures required for conventional superconductors is costly. The discovery of high-temperature superconductors in the 1980s expanded the horizon. Ceramic materials containing copper and oxygen planes were found to superconduct at temperatures far above those predicted by BCS theory, some above the boiling point of liquid nitrogen. The mechanism is still debated, with electron correlations, spin fluctuations, and lattice effects all implicated. These materials open possibilities for practical power transmission, magnetic levitation, and other uses, though challenges of fabrication and stability remain. More recently, iron-based superconductors and hydrides under extreme pressure have pushed critical temperatures higher still, hinting that room temperature superconductivity might one day be achieved. If stabilized under ordinary conditions, such a breakthrough could transform energy infrastructure, eliminating resistive losses and enabling technologies yet unimagined. Superfluidity, while related, arises in a different context. In 1937, two groups studying liquid helium-4 at temperatures near 2 Kelvin observed a sudden transition. Below that temperature, the liquid began to flow without viscosity, creeping up the walls of containers, sustaining persistent currents in thin films, and conducting heat with astonishing efficiency. This phase became known as the superfluid state. The explanation, given later by Lev Landau and others, built on the idea that helium atoms, being bosons, can undergo Bose-Einstein condensation. However, unlike dilute gases that condense at nanokelvin temperatures, liquid helium is dense and strongly interacting. The condensation is not of individual atoms but of a collective state where a macroscopic fraction of the system occupies a coherent ground state. Superfluid helium displays striking phenomena. A container of superfluid will exhibit the fountain effect, in which heat applied at one spot drives a counterflow of liquid that rises against gravity. It can sustain quantized vortices, thin filaments around which the phase of the superfluid wave function wends by integer multiples of 2p. These vortices interact and form tangles that lead to quantum turbulence, a state where the liquid churns in ways analogous to ordinary turbulence, but governed by quantization. Superfluidity is not merely an absence of resistance, it is the emergence of new hydrodynamics dictated by coherence and quantization. Helium-3, an isotope with 2 protons and 1 neutron, provides a contrasting example. Its atoms are fermions, so they cannot condense directly. Yet at millikelvin temperatures, they form Cooper pairs, analogous to electrons in superconductors. These pairs condense into a superfluid state with multiple phases distinguished by the symmetry of the pairing. Superfluid helium-3 thus unites themes of fermionic pairing and bosonic condensation, and its study has illuminated connections between condensed matter and particle physics, including analogies with symmetry breaking in the early universe. The relationship between superconductors and superfluids is more than superficial. Both rely on condensation into a coherent quantum state, whether of Cooper pairs or bosonic atoms. Both expel disturbances that would ordinarily dissipate energy. Both sustain quantized excitations that reveal their quantum character, yet they differ in the carriers of coherence. Electrons in metals for superconductors, neutral atoms in liquids for superfluids. This distinction shapes their experimental manifestations, but not the underlying principle that coherence across macroscopic scales can defeat resistance. In laboratories, superfluids and superconductors have become fertile grounds for exploring quantum phenomena. Rotating superfluids create arrays of vortices that resemble the magnetic flux lines in superconductors, demonstrating the universality of quantization. Thin superconducting films and cold atom condensates have revealed Berezinski-Kosterlitz-Thouless transitions, where vortex-antivortex pairs unbind in 2 dimensions. These studies connect microscopic quantum rules to emergent topological defects and collective excitations. They show that matter without resistance is not just a curiosity, but a window into the organizing principles of quantum many-body systems. Applications of superconductors are already significant. Beyond MRI and particle accelerators, superconducting materials are used in sensitive detectors for astronomy, in power cables for efficient energy transfer, and in prototype fusion reactors, where powerful magnets are required to confine plasma. Quantum technologies increasingly rely on superconducting circuits that exploit Josephson junctions to create qubits, resonators, and amplifiers. These qubits are among the most advanced platforms for quantum computing, leveraging coherence and controllability to perform complex operations. Superfluids, though less technologically exploited, may one day find roles in ultra-sensitive gyroscopes or cooling technologies, and they continue to inspire analogies and insights across physics. Superconductors and superfluids also illuminate the boundary between microscopic rules and macroscopic phenomena. That an electrical current can flow without loss, or that a liquid can defy viscosity, are not trivial outcomes of fundamental laws. They are emergent phenomena, arising only when countless particles act coherently. Dissipation, so common in our experience, turns out not to be inevitable, but contingent on whether coherence survives. In these systems, quantum mechanics refuses to be confined to the microscopic, instead manifesting in behaviors we can see, measure, and even use. The study of these states continues to evolve. Unconventional superconductors challenge our understanding of pairing mechanisms. Exotic superfluids raise questions about the role of dimensionality, disorder, and interactions. New materials under high pressure or engineered in laboratories push the boundaries of what conditions can sustain resistance-free states. The possibility of room temperature superconductivity, still debated, remains one of the great goals of physics and materials science. Its realization would be not just a technological leap, but a profound demonstration of how deeply coherence can reshape matter. In contemplating superconductors and superfluids, one finds a quiet existential lesson. The ordinary expectation of resistance, of energy lost and motion slowed, is not the only way matter can be. Under the right conditions, the world permits flows that do not fade, coherence that does not break. Nature allows resistance to vanish, not through isolation, but through collective unity. In these states, countless particles align into harmony, and the result is permanence, currents and flows that seem to transcend time. If there is a metaphor here, it is that sometimes unity can overcome the friction of existence, and motion, once begun, need not always end. Chapter 6. Quark-Gluon Plasma, Matter Before the Universe Cooled. If we try to imagine the universe in its earliest moments, before stars and galaxies, before even atoms or nuclei, we must picture a sea of matter so hot and dense that the familiar building blocks of protons and neutrons could not exist. Instead of stable particles, the universe was filled with their constituents, quarks and gluons, moving freely in an extreme fluid. This state of matter is called quark-gluon plasma. It is not simply an academic concept, but a phase that once dominated the cosmos during the first microseconds after the Big Bang, and one that physicists have recreated in modern particle colliders. Studying quark-gluon plasma is a way to look back into the universe's first instance and to confront the limits of our understanding of the strong nuclear force, one of the four fundamental interactions of nature. Ordinary matter around us is made of hadrons, particles such as protons and neutrons bound by the strong force. That force is carried by gluons, which mediate interactions between quarks. Unlike electromagnetism, where charged particles can be isolated, the strong force confines quarks permanently within hadrons. Attempts to pull quarks apart only create new pairs of quarks and antiquarks, ensuring that free quarks are never seen in isolation. This confinement is one of the most striking features of quantum chromodynamics, the theory describing strong interactions. Yet theory also suggests that at sufficiently high temperatures or densities, confinement can be overcome. The quarks and gluons can be liberated into a plasma state where they roam freely over distances larger than the size of a hadron. The early universe reached those conditions naturally. Within the first millionth of a second after the Big Bang, temperatures exceeded 1 trillion degrees, far hotter than the core of any star. At such energies, matter could not exist as bound nucleons. Instead, quark-gluon plasma filled space, a seething medium where quarks of all flavors and gluons interacted in a dense, strongly coupled soup. As the universe expanded and cooled, this plasma underwent a phase transition, confining quarks into the protons and neutrons that would later form nuclei, atoms, and eventually the material world we know. Understanding this transition is central to cosmology because it marks the point where the underlying components of matter took their permanent form. Creating quark-gluon plasma in the laboratory requires reproducing those extreme conditions. Modern heavy-ion colliders such as the Relativistic Heavy Ion Collider, RHI, in the United States and the Large Hadron Collider, LHC, at CERN accelerate heavy nuclei, gold or lead, to nearly the speed of light and smash them together. In the fleeting moment of collision, energy densities rival those of the early universe. For a tiny fraction of a second, a droplet of quark-gluon plasma is formed before it cools and hadronizes into a spray of detectable particles. The plasma cannot be observed directly, but its properties are inferred from patterns of particle production, correlations, and flow. What has emerged from these experiments is both surprising and profound. Quark-gluon plasma is not a weakly interacting gas, as once expected, but a nearly perfect fluid. It flows with extremely low viscosity, meaning it resists shear less than any other known substance. The evidence comes from the way particle distributions exhibit elliptic flow, reflecting collective motion consistent with hydrodynamics. This fluid-like behavior suggests that even at extreme temperatures, quarks and gluons remain strongly correlated, interacting in ways that defy the idea of a simple plasma of free particles. The discovery of this strongly coupled quark-gluon plasma was one of the landmark results of modern nuclear physics. Theoretical understanding of quark-gluon plasma relies on lattice quantum chromodynamics, a numerical approach where space and time are discretized and the equations of QCD are solved using supercomputers. These calculations show how confinement breaks down at high temperature and how the plasma transitions back to hadronic matter. They predict a critical temperature of around 150 to 170 mV, corresponding to about 2 trillion degrees Kelvin. They also explore the possibility of a critical point in the phase diagram of QCD, where the nature of the transition changes from a smooth crossover to a first-order phase transition. Finding experimental evidence of this critical point is a major goal of ongoing heavy-ion research. The physics of quark-gluon plasma also connects to other extreme environments. In the interiors of neutron stars, densities may be high enough to deconfine quarks, producing phases of quark matter or color superconductivity. Collisions of neutron stars, now observed through gravitational waves, may briefly create quark-gluon plasma conditions before ejecting material into space. These astrophysical contexts link laboratory experiments to cosmic events, showing how the same fundamental physics plays out across scales of time and space. Another striking feature of quark-gluon plasma is its opacity to energetic quarks and gluons. When high-energy partons traverse the plasma, they lose energy through interactions, a phenomenon known as jet quenching. This results in suppressed production of high-momentum particles compared to expectations from proton-proton collisions. Jet quenching provides a diagnostic of the plasma's density and coupling strength, offering clues about how quarks and gluons propagate through this unusual medium. Similarly, quarkonia, bound states of heavy quark-antiquark pairs, like charmonium or bottomonium, are suppressed in quark-gluon plasma because the screening of color charges prevents their formation. These signals form part of the experimental toolkit for probing the plasma's properties. Quark-gluon plasma is remarkable not only for what it reveals about the early universe, but also for what it teaches us about emergence. From a theoretical point of view, the strong nuclear force is a quantum field theory with well-defined rules. Yet the behaviors that emerge, confinement at low energies, nearly perfect fluidity at high energies, are not obvious consequences of those rules. They arise collectively from the interaction of countless degrees of freedom. In this sense, quark-gluon plasma is a case study in how simple laws generate complex phenomena, bridging the gap between fundamental theory and macroscopic reality. Despite advances, many mysteries remain. How exactly does the plasma thermalize so quickly after a collision? What are the microscopic mechanisms behind its low viscosity? Is there indeed a critical point in the QCD phase diagram, and can experiments find it? These questions drive both experimental programs and theoretical innovations, including attempts to use holographic duality from string theory to model strongly coupled plasmas. Such approaches treat the plasma as dual to a gravitational system in higher dimensions, offering new perspectives on an otherwise intractable regime. The effort to study quark-gluon plasma also illustrates the symbiosis of technology and science. Building machines capable of colliding heavy ions at relativistic speeds requires international collaborations, sophisticated detectors, and computing resources on a grand scale. Each collision produces thousands of particles, demanding complex reconstruction algorithms and statistical analysis. Yet from this torrent of data emerges a picture of a state of matter that existed before atoms, before nuclei, before the familiar world. It is as close as we can come to creating conditions of the newborn universe in a laboratory. The story of quark-gluon plasma is therefore a story of origins. It is about how matter behaved before cooling gave it structure, about how the most fundamental constituents interacted when unbound. By recreating this plasma, we peer through time to an epoch otherwise inaccessible, connecting experimental fireballs in colliders to the cosmic fireball of the Big Bang. In doing so, we are reminded that the matter we know is not the only possibility. Just as solids, liquids, gases, and plasmas are not exhaustive, even protons and neutrons are not the ultimate containers of matter's identity. There are states deeper, stranger, and more fleeting that nonetheless shape the history of the universe. In an existential sense, quark-gluon plasma embodies the idea that everything familiar is contingent. The atoms that compose our bodies, the structures that form stars and planets, emerged only because the plasma of the early universe cooled and confined. Before that, individuality did not exist. Only a vast, seething medium where boundaries were meaningless. To contemplate this state is to recognize that the solidity of matter is a temporary arrangement, one phase among many. In the end, matter is not fixed but fluid, capable of transformations as radical as quarks and gluons finding themselves bound, and from that binding, everything else unfolding. Chapter 7. Exotic Magnetism, Spin Liquids and Topological Phases. Magnetism is one of the most familiar phenomena in physics, known since antiquity and encountered daily in everything from compass needles to computer hard drives. At a fundamental level, magnetism originates in the spins of electrons and their orbital motions around nuclei. In most magnetic materials, spins do not remain isolated but interact with one another through exchange interactions, which arise from the quantum mechanical overlap of electronic wave functions. These interactions can align spins parallel, as in ferromagnets, or antiparallel, as in antiferromagnets. The result is long-range magnetic order, a collective alignment that persists across macroscopic scales. Yet there are situations where such ordering never occurs, even at temperatures approaching absolute zero. Instead, spins remain in a state of perpetual fluctuation, refusing to settle into any conventional pattern. These are quantum spin liquids, one of the most intriguing examples of exotic magnetism, and they form a bridge to the broader world of topological phases of matter. The term spin liquid was first proposed in the 1970s by Philip Anderson, who suggested that frustration and quantum fluctuations might prevent spins from freezing into order. Frustration in this context does not mean irritation, but a geometric impossibility. If spins interact in ways that cannot be simultaneously satisfied, no single arrangement minimizes energy for all bonds. The classic example is a triangular lattice with antiferromagnetic interactions. Place one spin up, the second must be down, but the third is left with no configuration that satisfies both neighbors. The system compromises by fluctuating, never settling into a single ground state. Quantum mechanics amplifies this frustration by allowing superpositions of spin configurations. In a quantum spin liquid, spins are entangled across the lattice, producing a ground state without static order, but with hidden correlations. The properties of quantum spin liquids are extraordinary. They exhibit long-range entanglement, meaning that correlations persist across the system even though no classical order is visible. They support emergent excitations that behave like particles, such as spinons carrying spin but no charge, or visons representing fluxes of emergent gauge fields. These excitations can obey exotic statistics beyond fermions and bosons, falling into the category of anyons. In 2 dimensions, anyons can interpolate between familiar particle types, and their braiding around one another can encode information in a way robust against local disturbances. This connection between spin liquids and anyonic excitations has made them central to ideas for topological quantum computing. Experimentally, realizing quantum spin liquids is challenging because many materials with frustrated interactions eventually order at low temperatures. Still, candidate systems exist. Certain organic salts, Kagome lattice compounds, and iridates exhibit behaviors consistent with spin liquid states, absence of magnetic ordering down to millikelvin temperatures, unusual heat capacity signatures, and spin excitations detected by neutron scattering or thermal transport. The mineral herbertsmithite, with its Kagome lattice of copper ions, is a leading candidate, showing fractionalized excitations and no ordering despite strong interactions. These materials offer glimpses into phases where magnetism becomes profoundly quantum, dominated not by alignment but by entanglement. Topological phases expand the landscape of exotic magnetism beyond spin liquids. In conventional phases of matter, order is described by local parameters: magnetization for ferromagnets, density for crystals, superfluid fraction for superfluids. Topological phases, however, are defined by global properties insensitive to local details. Their ground states cannot be distinguished by symmetry breaking, but by invariants that remain fixed unless the system undergoes a drastic change, such as closing an energy gap. The fractional quantum Hall effect, discovered in the 1980s, is the archetype. Electrons confined to 2 dimensions under a strong magnetic field form a correlated state where the Hall conductance is quantized in fractions of fundamental units. The excitations of this state carry fractional charge and obey anyonic statistics, phenomena explained only by invoking topological order. The link between spin liquids and topological phases becomes clear when we recognize that both embody emergent gauge theories and fractionalized excitations. In a spin liquid, the lack of classical order hides a deeper organization. The system behaves as if governed by an emergent gauge field, with spinons and visons as its charges and fluxes. This emergent structure cannot be described by any local order parameter, but it manifests in measurable ways, such as unusual low-temperature heat capacities or specific patterns of entanglement entropy. Similarly, in topological phases like the fractional quantum Hall state, the robustness of edge states and fractional charges derives from topological order. These are not rare exceptions, but evidence of a new paradigm. Matter can organize not only by breaking symmetries, but by weaving topological patterns invisible to classical probes. Theoretical models have played a crucial role in developing these ideas. The Kitaev model, introduced by Alexei Kitaev in 2006, describes spins on a honeycomb lattice interacting through bond-dependent anisotropic couplings. Remarkably, this model can be solved exactly, and it yields a spin-liquid ground state with excitations that are Majorana fermions coupled to an emergent gauge field. In certain regimes, these excitations become non-abelian anyons, whose braiding could provide fault-tolerant qubits for quantum computation. Materials resembling Kitaev's model, such as ruthenium and iridium-based compounds, have since been synthesized, and while they may not realize the model perfectly, they exhibit hints of Kitaev-like physics. These connections between abstract models, candidate materials, and future technologies highlight the fertile interplay of theory and experiment in the study of exotic magnetism. The significance of topological phases extends beyond magnetism. Topological insulators, first predicted and then observed in the 2000s, are materials whose bulk is insulating but whose surfaces conduct robustly due to topological protection. These surface states are resistant to scattering from impurities because their existence is tied to the topology of the electronic band structure. Topological superconductors, similarly, host edge or surface modes that may harbor Majorana fermions. While these systems extend beyond spin liquids, the unifying theme is clear. Topology provides a way of classifying phases of matter that transcend symmetry and order parameters. Exotic magnetism is thus part of a larger revolution in condensed matter physics, one that reframes our understanding of what a phase of matter can be. From a broader perspective, the discovery of spin liquids and topological phases shows how magnetism, once thought of as a well-understood branch of physics, remains a frontier. For centuries, magnetism was associated with simple alignment. In ferromagnets, spins point together. In antiferromagnets, they alternate. But in these exotic states, the story is different. Spins fluctuate endlessly, entangle in patterns invisible to classical order, or give rise to emergent particles with properties alien to our intuition. Magnetism is no longer about arrows frozen in patterns, but about quantum entanglement sculpting reality at macroscopic scales. These phases also reveal the power of emergence. Fractional charges, anyons, and topological invariants are not written into the equations of electrons and spins in any obvious way. They arise collectively from the subtle dance of many particles in constrained geometries. In this sense, exotic magnetism exemplifies one of physics' deepest lessons. The laws of nature are not exhausted by fundamental interactions, but enriched by the collective phenomena they permit. What appears impossible for a single spin, fractionalization, long-range entanglement, becomes natural for billions acting in concert. Despite the progress, much remains unknown. Experimentally proving the existence of spin liquids is difficult because their defining property is the absence of order. Identifying topological order requires indirect probes, such as patterns of entanglement entropy or braiding statistics, which are hard to measure. The search for materials realizing ideal models continues, with chemists and physicists designing lattices and interactions to engineer frustration and entanglement. The hope is not only to confirm theoretical predictions, but to harness these phases for technology, particularly quantum computing, where robustness to local disturbances is invaluable. As the study of exotic magnetism advances, it intersects with other frontiers. Cold atom experiments now simulate frustrated lattices and gauge fields, offering ways to realize spin liquids in controllable settings. Photonic and mechanical systems are being engineered to mimic topological band structures, extending the concept of topological phases beyond electronic materials. These cross-disciplinary explorations suggest that the principles uncovered in exotic magnetism may apply universally, wherever waves and interactions combine in constrained geometries. The fascination of exotic magnetism lies not only in its scientific content, but in its philosophical resonance. A spin liquid is order without order, a state defined not by visible patterns, but by hidden coherence. A topological phase is stability without symmetry, a robustness that arises from structure at the deepest level of a system's quantum description. Together, they remind us that reality can hide complexity beneath simplicity, that absence of pattern may mask a deeper kind of order. In an existential sense, these states suggest that coherence and meaning are not always visible on the surface. Just as spins may be entangled in ways that leave no classical trace, so too can the universe hold structures that evade simple description. The hidden order of spin liquids and the invisible invariance of topological phases whisper that not all truths are obvious, yet they shape the behavior of the whole. To sleep with this thought is to drift into a universe where even the unseen may be the most real, and where the quiet patterns of entanglement hold matter, and perhaps existence itself, together. Chapter 8. Strange Insulators and Conductors, Topological Materials. For much of modern physics, the understanding of solids has been dominated by band theory. In this framework, the behavior of electrons in a crystal is explained by the way their allowed energy levels form continuous bands, separated by forbidden regions known as gaps. Metals conduct electricity because their highest band is only partially filled, allowing electrons to move when an external voltage is applied. Insulators do not conduct because their bands are completely filled, leaving no available states for electrons to occupy without surmounting a large gap. Semiconductors, so central to modern electronics, occupy an intermediate position, with gaps small enough to be bridged by thermal excitation or doping. For decades, this classification seemed complete, yet it missed something profound: the role of topology, the mathematics of global structure, in determining material behavior. The discovery of the quantum Hall effect in the 1980s cracked open this view. When electrons are confined to two dimensions and subjected to strong magnetic fields at very low temperatures, their transverse conductance does not vary smoothly, but locks into precise integer values. Even when impurities or imperfections are present, the quantization is exact to astonishing accuracy, better than 1 part in a billion. This robustness suggested that something deeper than ordinary band filling was responsible. A few years later, the fractional quantum Hall effect revealed even stranger behavior, with conductance taking on fractional values and excitations carrying fractional charges. Both phenomena pointed to a new organizing principle: topological invariance. Unlike local order parameters such as magnetization, which can vary with small changes, topological invariants remain fixed, unless the system undergoes a dramatic transformation, such as closing an energy gap. The mathematics underlying this robustness draws from topology, which classifies objects based on global properties rather than local details. A coffee cup and a donut are equivalent in topology because each has one hole. Their shapes can be deformed into each other without cutting. Similarly, electronic wave functions in solids can be characterized by invariants such as Chern numbers, which remain constant under smooth deformations. In the quantum Hall effect, the Hall conductance corresponds directly to a Chern number, explaining its stability against impurities. This was the first sign that topology could determine electronic properties in ways untouched by conventional band theory. The field expanded further in the 2000s with the theoretical prediction of topological insulators. These are materials that, by all ordinary measures, should be insulators. Their bulk has a full band gap, preventing conduction. Yet their surfaces or edges conduct with remarkable resilience. This paradoxical combination arises from the topology of the electronic bands. Strong spin-orbit coupling twists the bands in such a way that the topological invariant describing them differs from that of a trivial insulator. Because the invariants cannot change without closing the band gap, the system must host conducting boundary states to resolve the mismatch between interior and exterior. The result is a material that is insulating in the bulk but metallic at its boundaries. Experiments soon confirmed these predictions. Bismuth-based compounds such as bismuth selenide and bismuth telluride were shown to exhibit robust surface states with Dirac-like dispersions, where electrons behave as if they are massless. Angle-resolved photoemission spectroscopy, which maps the relationship between energy and momentum of electrons, revealed the linear band crossings characteristic of topological insulators. Transport measurements confirmed that these states were resistant to scattering, persisting even in imperfect samples. The discovery ignited enormous interest, not only for its novelty, but for its implications. Here was a new phase of matter, defined not by broken symmetry, but by hidden topological structure. The robustness of topological surface states lies in time reversal symmetry. In topological insulators, the electron's spin is locked to its momentum, a phenomenon known as spin-momentum locking. Backscattering, where an electron reverses direction, would require flipping spin. If time reversal symmetry is preserved, such processes are forbidden. This protection explains why conduction at the surface is so stable against impurities. It also points to applications in spintronics, where electronic devices could exploit spin directly rather than relying on charge alone. Beyond insulators, topology has given rise to a zoo of new materials. Topological semimetals, such as Dirac and Weil semimetals, feature conduction and valence bands that touch at discrete points in momentum space. Near these nodes, electrons behave as relativistic particles with linear dispersion relations, mimicking solutions of the Dirac or Weil equations from high-energy physics. These materials exhibit high carrier mobility, unusual magnetoresistance, and phenomena tied to the chiral anomaly, where imbalances in particle populations are created when electric and magnetic fields are aligned. In effect, tabletop experiments can probe physics once thought confined to particle accelerators. Another frontier is topological superconductivity. When superconductivity combines with topological band structures, exotic boundary modes can appear. Among the most tantalizing are Majorana zero modes, quasi-particles that are their own antiparticles. Their statistics are non-abelian. Exchanging two Majoranas alters the system's state in a way that depends on the sequence of exchanges. This makes them candidates for fault-tolerant quantum computing, where information is stored non-locally and is thus protected from many forms of decoherence. Experiments in semiconductor nanowires coupled to superconductors have produced signatures consistent with Majorana modes, though definitive proof remains a major goal. The reach of topology in materials science extends still further. Photonic crystals, designed structures that control the propagation of light, have been engineered to host topological edge states, allowing light to travel around corners without scattering. Mechanical metamaterials have been built to support topologically protected vibrational modes, resilient to defects. Even cold atoms in optical lattices have been arranged to simulate topological band structures, offering highly tunable platforms for exploring theoretical predictions. These realizations underscore the universality of topology. Whether in electrons, photons, or phonons, the underlying mathematics ensures that global invariants dictate robust behavior. The practical potential of topological materials is substantial. Low dissipation electronics could exploit surface states that resist scattering. Spintronic devices could harness spin momentum locking for efficient information processing. Quantum computers could leverage Majorana modes for error-resistant qubits. In photonics, robust edge modes could yield optical circuits immune to fabrication defects. Even in mechanical systems, topological design could produce structures with vibrations confined to desired paths, useful in engineering and architecture. The field is still young, but its fusion of abstract mathematics and tangible utility is one of the most striking trends in modern physics. Despite progress, many questions remain unresolved. Can topological materials be engineered to function at room temperature, where practical applications would flourish? How do strong electron-electron interactions modify topological phases, perhaps giving rise to new states not yet classified? Can we systematically design materials with desired topological invariants, rather than relying on serendipity? The search for answers drives a vibrant interplay between theory, experiment, and materials science. Topological phases also reshape how physicists think about classification. The old paradigm of symmetry breaking remains powerful, but it is no longer the only way to categorize matter. Topology introduces a second axis of classification, one that deals not with local arrangements, but with global structure. This dual framework has expanded the conceptual map of phases of matter, making room for states that would otherwise appear paradoxical. A material can be both an insulator and a conductor, both inert in its bulk and vibrant on its surface. The paradox dissolves once we recognize that topology dictates new possibilities. The subtlety of topological materials carries philosophical resonance. Their novelty is not visible to the naked eye. A topological insulator looks like an ordinary crystal. Its strangeness lies hidden in the structure of wave functions, in invariants that cannot be altered by small disturbances. This is a reminder that the most consequential features of reality may not announce themselves loudly. They may be buried in hidden structure, global rather than local, shaping outcomes in ways invisible without careful probing. From a broader perspective, the rise of topological materials exemplifies the capacity of physics to uncover new order where none was expected. A generation ago, it seemed that the classification of solids was nearly complete. Today, we recognize that the landscape of phases is vastly larger, populated by states defined by topology, entanglement, and global invariance. The boundary between insulators and conductors is not sharp, but laced with new possibilities, bridging mathematics and matter in ways that continue to unfold. And in a softer register, there is an existential echo. These materials teach us that hidden structure can confer strength, that what appears fragile can in fact be robust if the whole is arranged in the right way. In life, as in matter, resilience sometimes arises not from local perfection, but from global coherence. The lesson of topological materials is that unseen patterns hold power, and that even the most ordinary crystal may conceal extraordinary order beneath its surface. Chapter 9. Nuclear and Astrophysical Matter, Neutron Stars, and Beyond. When we look at matter in everyday life, it seems familiar and manageable. Solids with rigid structures, liquids that flow, gases that expand, and plasmas that glow. Yet in the densest corners of the universe, matter is pushed into regimes so extreme that it cannot resemble anything on Earth. There, the physics of nuclei, quarks, and degenerate quantum fluids dominates. The most striking examples are neutron stars, compact remnants left after the collapse of massive stars. These objects are not exotic in the sense of being rare curiosities. They are abundant in the galaxy. But they are exotic in how radically they redefine what matter can be when subjected to crushing gravitational forces. Studying nuclear and astrophysical matter, especially in neutron stars and their kin, reveals the richness of the phase diagram of the universe, extending far beyond anything we can reproduce in a laboratory. Neutron stars are born in the fiery deaths of massive stars. When a star more than about 8 times the mass of the Sun exhausts its nuclear fuel, its core can no longer support itself against gravity. The outer layers explode in a supernova, while the core collapses. If the remaining mass is not sufficient to form a black hole, it stabilizes as a neutron star. The radius is typically around 10 to 12 kilometers, yet the mass is between 1 and 2 times that of the Sun. This means that a neutron star packs more matter than the Sun into a sphere only the size of a city. The resulting densities are immense, exceeding those of atomic nuclei. A single teaspoon of neutron star matter would weigh billions of tons. In this environment, atoms cannot exist. Electrons are forced into protons, creating neutrons through inverse beta decay. The star becomes, to first approximation, a giant nucleus. But the details are more subtle and more fascinating. The outermost layers of a neutron star form a crust where nuclei, still present but highly neutron-rich, are arranged in a lattice. As one descends inward, the density rises and free neutrons drip out of the nuclei, forming a neutron fluid that coexists with nuclear clusters. Deeper still, the crust gives way to a core dominated by neutrons, but with a significant admixture of protons, electrons, and muons. At these densities, neutrons are expected to form a superfluid, while protons may form a superconducting fluid. The existence of superfluidity in neutron stars is not mere speculation. It explains observed phenomena such as pulsar glitches, sudden jumps in the rotation of neutron stars. These glitches are believed to occur when superfluid vortices pinned in the crust suddenly unpin and transfer angular momentum to the outer layers, producing detectable changes in timing. The inner core of a neutron star is even less certain. At densities several times higher than nuclear matter, new degrees of freedom may appear. Hyperons, particles containing strange quarks, might become energetically favored, softening the equation of state. Alternatively, quarks themselves might deconfine, creating a phase of quark matter, or even a color superconducting phase where quarks pair in analogies to Cooper pairing in ordinary superconductors. The exact nature of this inner core remains one of the great unknowns of modern astrophysics. Observational data, such as precise mass and radius measurements, or gravitational wave signals from neutron star mergers are beginning to constrain possibilities, but the landscape is wide open. The matter inside neutron stars is a laboratory for physics that transcends nuclear science, pushing into the realm of fundamental questions about quark-gluon dynamics. The physics of nuclear matter also extends to phenomena in heavy ion collisions on Earth. In colliders such as the relativistic heavy ion collider and the Large Hadron Collider, nuclei are smashed together at relativistic speeds, creating conditions that momentarily probe densities and temperatures akin to those in neutron star interiors or the early universe. While these experiments cannot create macroscopic objects like neutron stars, they provide insight into the equation of state of nuclear matter, the phase transition from hadronic to quark matter, and the transport properties of strongly interacting systems. The synergy between laboratory collisions and astrophysical observations is essential. Each informs the other, building a picture of matter across extremes. Observations of neutron stars continue to challenge theory. For instance, the discovery of neutron stars with masses around 2 solar masses places strong constraints on the equation of state. It rules out overly soft equations of state that would collapse under such mass. Gravitational wave detections of neutron star mergers, most famously GW17U817, provide further clues. The tidal deformability inferred from such events depends sensitively on the stiffness of neutron-rich matter. Electromagnetic counterparts, such as kilonovae powered by the radioactive decay of heavy elements produced in the merger, add another layer of information. These multi-messenger observations knit together nuclear physics, astrophysics, and cosmology, offering unprecedented opportunities to probe matter under conditions otherwise inaccessible. Neutron stars are not the only environments where nuclear and astrophysical matter shows its extremes. White dwarfs, while less dense, illustrate the role of electron degeneracy pressure, where the exclusion principle of electrons halts gravitational collapse. In neutron stars, it is neutron degeneracy and nuclear forces that provide support. At still higher masses, even these pressures fail, leading to black holes where matter is crushed beyond recognition. Between these regimes lies a fascinating spectrum of possibilities, including hybrid stars with quark cores or stars dominated by hyperons. Each possibility is a different solution to the problem of balancing gravity against the forces and quantum principles that operate at the smallest scales. The study of such matter has practical significance beyond curiosity. The production of heavy elements in the universe, gold, platinum, uranium, likely originates in neutron star mergers, where neutron-rich matter is ejected and undergoes rapid neutron capture, the R process. This cosmic alchemy links the behavior of matter under extreme density to the chemical evolution of galaxies and planets, and ultimately to the composition of our bodies. Every heavy element in our jewelry, our electronics, and our DNA carries the imprint of nuclear astrophysics, a testimony to the power of extremes. From a theoretical standpoint, describing nuclear and astrophysical matter requires tools that blend quantum mechanics, relativity, and statistical physics. Quantum chromodynamics, the fundamental theory of the strong force, is difficult to apply directly at the relevant densities. Instead, effective field theories, phenomenological models, and numerical approaches like lattice QCD are combined with astrophysical constraints. The interplay between microphysics and macrophysics is unavoidable. The stiffness of nuclear matter affects the maximum mass of neutron stars. The pairing gaps of neutrons and protons determine cooling rates via neutrino emission. The presence or absence of exotic phases influences gravitational wave signals. Each detail of nuclear physics reverberates across astronomical scales. The richness of nuclear and astrophysical matter also illustrates the idea of emergence. At low density, we see nuclei, discrete bound states of protons and neutrons. At higher density, we see nuclear matter, a fluid of nucleons interacting strongly. At still higher density, we may see quark matter, where nucleons dissolve into their constituents. These are not separate theories, but phases of the same underlying theory, revealed as conditions change. The universe itself is a machine that explores this phase diagram, producing white dwarfs, neutron stars, and black holes as outcomes of stellar evolution. Our role is to interpret these experiments, reading nature's results through the light of telescopes and the signals of detectors. Despite remarkable progress, much remains uncertain. Do neutron stars universally contain quark cores, or are they rare exceptions? Is there a sharp phase transition between hadronic and quark matter, or a smooth crossover? Where is the critical point in the QCD phase diagram, if one exists? How does nuclear superfluidity shape pulsar behavior? These questions remind us that even familiar matter can become profoundly strange under pressure, and that the universe holds laboratories far beyond what we can build. In reflecting on nuclear and astrophysical matter, we glimpse the interconnectedness of scales. The same exclusion principle that arranges electrons in atoms prevents stars from collapsing. The same nuclear interactions that bind protons and neutrons together determine the fate of entire stellar remnants. The same physics that governs laboratory nuclei dictates whether gravitational waves echo across the cosmos. Matter is one, even when stretched to its most alien forms. And here, an existential thought finds its place. Neutron stars, so distant and so unlike the world we know, are reminders that matter can be many things. Our bones and blood are one arrangement, the crust of a neutron star is another. Both emerge from the same laws, both are temporary solutions to the constraints of energy and symmetry. To know that the universe can take matter and press it into a form where individuality of particles dissolves into collective quantum states is to sense that our familiar reality is only a narrow slice of possibility. Beneath us, around us, and far beyond us, matter is always more than it seems. Chapter 10. The Frontier of Matter. What else might exist? The catalog of matter we have assembled is impressive, yet by every indication it is unfinished. The same equations that describe crystals and liquids, plasmas and condensates, also permit arrangements that are only now being glimpsed in the laboratory, and others that may never occur in nature but can be built deliberately. The frontier is not a single boundary, but a broad region where our classifications are stretched by conditions we have only recently learned to create. Ultra-low temperatures and ultra-high pressures, exquisitely clean environments, programmable interactions, and precision drives that hold systems far from equilibrium without letting them fall apart. Each of these corridors exposes a new piece of the phase diagram, and along those corridors, novel states of matter appear. One axis of exploration is extreme control over quantum matter. Ultra-cold atom platforms now allow precise tuning of dimensionality, interaction strength, and disorder. Optical lattices draw crystals of light in which neutral atoms play the role of electrons, but without impurities or unknown couplings. In these clean arenas, phases predicted decades ago have been stabilized, and wholly new ones have appeared. Supersolids, states that combine crystalline density modulation with phase-coherent flow, have been realized by coupling Bose-Einstein condensates to optical fields that cede periodic order while preserving superfluidity. Discrete time crystals, where observables oscillate at a subharmonic of the drive and remain phase coherent against perturbations, have emerged in driven spin systems and trapped ion arrays. They are not perpetual motion machines, but out-of-equilibrium phases stabilized by disorder or prethermal plateaus, expanding the very meaning of phase to include dynamical order rather than a static arrangement. Another axis is strong correlation, where interactions rather than single particle motion set the rules. A striking case is moire matter. When two atomically thin crystals such as graphene are rotated by a small angle, a long wavelength interference pattern creates flat electronic bands. In these bands, the kinetic energy is quenched and even modest Coulomb repulsion becomes dominant, producing correlated insulators, low-density superconductors, ferromagnetism, and topological churn insulating phases controlled by electric fields. The landscape is tunable with twist angle, pressure, and gating, transforming a stack of familiar materials into a laboratory for emergent order. The lesson is broad. By engineering band geometry, flattening dispersions, enhancing Berry curvature, or tailoring Van Hove singularities, one can sculpt the phase diagram and promote interactions to center stage. Similar strategies are spreading to transition metal dicogenide heterostructures, where flat band physics is now a central theme. Topological matter itself continues to diversify. Beyond the now familiar topological insulators lie higher-order topological phases, in which protected gapless modes live not on surfaces, but on hinges or corners, reflecting a more intricate bulk boundary correspondence. Nodal line and nodal chain semimetals host extended band-touching manifolds rather than isolated points, shaping unusual responses to fields in disorder and giving rise to drumhead surface states. In magnetic systems, topological magnons, quantized spin waves with non-trivial band topology, can carry chiral edge heat currents immune to backscattering, while skyrmion lattices provide particle-like, topologically protected textures that can be moved by tiny currents. Even phonons, classically neutral vibrations of a lattice, can acquire topological character when symmetry and geometry align. These developments underscore that topology is not a property reserved for electrons. It can be imprinted into the dynamics of electrons, spins, and even vibrations. A different branch of the frontier departs from strictly Hermitian quantum mechanics to explore systems where gain and loss are engineered at the microscopic level. In photonic and phononic metamaterials, non-Hermitian band structures host exceptional points at which eigenvectors coalesce. Near these singularities, response functions are highly sensitive to perturbations, enabling lasers with unconventional line-width control, unidirectional invisibility, and sensors that approach quantum limits. Parity-time symmetric phases balance gain and loss to realize real spectra in open settings, blurring the boundary between dissipation and Hamiltonian dynamics. Non-Hermitian topological phases extend bulk boundary correspondence to systems that exchange energy with their environment, recovering robust edge modes even when probability is not conserved. These discoveries widen the classification of phases to include global structures in the space of non-Hermitian operators. Disorder, long treated as a nuisance, has become a resource. Many-body localization provides a mechanism by which interacting systems avoid thermalization, preserving quantum memory at high energy densities and stabilizing out-of-equilibrium order such as discrete time crystals. Closely related ideas, Hilbert space fragmentation, in which local constraints partition the accessible set of many-body states, quantum scars, where atypical, weakly entangled eigenstates punch through an otherwise thermal spectrum, and long-lived prethermal plateaus in rapidly driven systems reveal still other ways for dynamics to remain structured in the face of interactions. These notions matter technologically because they offer routes to protecting coherence without refrigeration to the ground state, and conceptually because they enlarge the taxonomy of phases to include dynamical classes defined by their approach to or avoidance of equilibrium. Quasi-particles with unfamiliar statistics are no longer confined to two-dimensional electron gases. Quantum simulators built from Rydberg atoms and superconducting qubits now implement lattice-gauge theories in which emergent anyons can be created and braided in programmable geometries. Hybrid superconductor semiconductor devices aim to localize Majorana zero modes, whose non-abelian exchange could encode topologically protected qubits, a path to fault-tolerant computation based on geometry rather than error syndromes. Spin-ice materials provide a complementary, more classical window on emergent gauge fields. Their frustrated magnetic moments behave as if magnetic monopoles fractionalize from the underlying spins and wander through a background Coulomb phase, revealing conservation laws and field lines in real time. Together, these platforms push exchange statistics from a theoretical curiosity into an experimental design variable. High-pressure physics continues to alter our picture of what the periodic table can do. Hydrogen, long predicted to metallize under immense compression, is now joined by hydrogen-rich alloys that superconduct at temperatures approaching or exceeding room temperature, albeit at multi-megabar pressures. These hydrides, stabilized by pressure, embody a conventional route to high-temperature superconductivity through strong electron-phonon coupling. The remaining challenge is to retain such phases at accessible pressures or find chemical analogs that mimic their bonding. Water, equally familiar at ambient conditions, reveals superionic phases at planetary pressures in which oxygen forms a crystalline sublattice, while hydrogen ions flow like a liquid, a state that likely shapes the magnetic fields of Uranus and Neptune. Even simple elements acquire unfamiliar valences and structures as orbitals reshuffle under compression, reminding us that the ordinary materials of daily life are exceptional points in a vast space of possibilities. Astrophysics pushes the frontier further. Ultra-dense matter in neutron star cores may harbor hyperons, deconfined quarks, or color superconducting phases with rich pairing symmetries. These possibilities are being constrained by precise mass and radius measurements, X-ray pulse profile modeling, and tidal deformabilities extracted from gravitational wave observations of neutron star mergers. Ultralight bosonic fields, axions or axion-like particles, if they exist, could form macroscopic Bose condensates on astrophysical scales. Around rapidly spinning black holes, such fields would grow by superradiance, forming clouds that back-react on the hole's spin and potentially radiate monochromatic gravitational waves. At still lower densities, self-gravitating bosonic configurations, boson stars or axion stars, could arise, compact objects supported not by degeneracy pressure, but by field gradients and self-interactions. None of these candidates has been confirmed, but each connects the microphysics of hypothetical particles to macroscopic observable structures. The dark sector more generally may admit a parallel chemistry. If dark matter carries charges under hidden gauge forces, it could bind into dark atoms, cool via dark photons, and form structures from dark molecular clouds to compact dark objects. Such matter would be invisible electromagnetically, yet potentially collisional and dissipative within its own sector, altering galactic morphologies and core dynamics. Conversely, if dark matter is ultralight, It may behave as a coherent wave, forming soliton-like cores and halos and supporting interference patterns on kiloparsec scales. Even without non-gravitational interactions, these scenarios lead to distinctive signatures in lensing, halo profiles, and small-scale structure. The frontier here is observational creativity. Precise, strong lensing maps, pulsar timing arrays, stellar stream perturbations, and 21-centimeter surveys each offer ways to test whether some fraction of the universe's invisible matter participates in its own phases. At the opposite extreme of density and energy, quantum field theory invites phases that mix matter with spacetime in unfamiliar ways. Near the Planck scale, the continuum picture of spacetime likely breaks down, and with it our standard notion of particles. Candidate theories of quantum gravity, string theory with its vibrating extended objects, causal dynamical triangulations with statistical ensembles of geometries, loop quantum gravity with discrete spin network states, suggest that geometry itself may be quantized or emergent. In holographic dualities, certain strongly coupled quantum systems are exactly equivalent to gravitational theories in one higher dimension. This correspondence has already paid dividends by modeling strongly coupled fluids, strange metals with Planckian dissipation, and quantum critical points that defy quasi-particle descriptions. While such dualities are not proofs that spacetime is emergent, they suggest that phases of matter and phases of geometry can mirror one another, offering calculational footholds where direct methods fail. Engineered matter has become a proving ground for such correspondences. Quantum circuits made from superconducting islands and semiconductors can be wired to produce effective Hamiltonians with tunable interactions, topology, and dissipation. Hybrid systems couple photons to excitons to form polaritons that condense or use cavity quantum electrodynamics to induce long-range interactions that drive self-organization transitions. Nonlinear photonic lattices realize synthetic magnetic fields for light, while reservoir engineering shapes dissipation so that the environment stabilizes desired quantum order rather than destroying it. Measurement itself can be promoted from a readout step to a control knob. In monitored quantum circuits, varying the rate and pattern of projective measurements drives entanglement phase transitions between volume law and area law regimes, phases defined not by energy spectra, but by patterns of quantum information. Out of this broad survey, a few themes recur. First, equilibrium is only a special case. Many of the most striking new phases, time crystals, prethermal ordered states, and measurement-stabilized topological order, live in driven, open, or monitored settings. Second, the low-energy degrees of freedom are design variables. By shaping band geometry, interaction range, constraint structure, and coupling to environments, we can sculpt the emergent quasi-particles and their statistics. Third, topology and entanglement provide classifications that remain robust when microscopic details are out of control, offering islands of predictability in the sea of complexity. These themes are methodological rather than taxonomic. They tell us how to search, not only what to search for. What, then, might we still be missing? Fracton phases, states in which elementary excitations cannot move freely alone but only in bound combinations, suggest that mobility itself can be an emergent, restricted resource encoded by higher-ranked gauge structures. Such phases exhibit ground state degeneracies that scale with system size, display elasticity-like responses, and feature glassy dynamics even at zero temperature. They are candidates for robust quantum memory and for unusual mechanical behavior where stress and charge intertwine. Non-ergodic metals, which conduct electricity yet exhibit subdiffusive dynamics and anomalously slow thermalization, hint that transport and thermalization can be decoupled more widely than expected. And beyond quasi-particles, some strongly entangled phases resist any description in terms of emergent particles, demanding field-theoretic or information-theoretic language from the outset. Some celebrated claims remind us to keep our standards high. Reports of ambient pressure, room temperature superconductivity have sparked excitement and skepticism in equal measure. Difficulties with independent reproduction and the occasional retraction underscore the importance of rigor. The history of the field shows that extraordinary states can be realized, but also that extraordinary evidence is required. This discipline is not a brake on discovery, but its ally, ensuring that when a new phase is admitted into the canon, it will endure. The frontier is therefore methodological as much as conceptual. New probes, ultrafast spectroscopies that resolve dynamics on femtosecond scales, quantum-limited sensors that detect single phonons or magnons, scanning probes that map current with nanometer resolution, gravitational wave detectors that reach higher frequencies, are expanding what can be seen. New computations, tensor network methods for entangled low-dimensional systems, unbiased quantum Monte Carlo in sign problem-free regimes, density functional and dynamical mean field methods refined by machine learning, and analog quantum simulators that replace intractable integrals with measurements on well-controlled devices, are expanding what can be calculated. Each advance converts a hypothetical phase into a testable one. It is tempting to search for a final taxonomy, a completed periodic table of phases. The sober lesson of the last few decades is that such closure is unlikely. Because phases depend on constraints, and because constraints can be engineered or encountered in nature in unbounded variety, the space of possible matter is effectively inexhaustible. The instructive question is not, what is the list? But what are the principles that organize the lists we will keep extending? Symmetry, topology, and entanglement structure provide three such principles, and to them we can add dynamics and geometry as independent axes along which phases can be grouped. This attitude accepts that any catalog is provisional, and that its purpose is to guide exploration, not to declare it complete. In the end, this frontier folds back on how we think about matter itself. Matter is not a single substance, but a choreography of degrees of freedom under rules that can be simple or baroque. The same Hamiltonian written in a different parameter regime can yield a crystal, a fluid, a superconductor, or a glass. A field that looks like a particle at one scale dissolves into waves at another. A vacuum that seems empty is discovered to seethe with fluctuations. Our classifications are maps, and like all maps, they omit detail to reveal structure. They will be redrawn as we learn new landmarks, and that is their purpose, to guide exploration. Two quiet thoughts to close. The solid ground beneath us is only one of many arrangements the universe chooses to sustain for a while. So are we, briefly coherent, shaped by context, patterns among patterns in a cosmos whose matter never runs out of ways to be. You've just traveled across the frontier of matter, from the familiar to the truly extraordinary. I hope the gentle pace of these ideas helped quiet your mind. If you're still awake and want to keep exploring, another video is waiting for you, ready to carry you deeper into the mysteries of the cosmos. But if sleep is already upon you, then let it take you gently. Sweet dreams, my friend, and may they be filled with stars.